thus far in Chapter 9, we have focused upon collision theory. We have also discussed reaction rates. And factors that impact reaction rates. We spent time thinking about concentration, thinking about temperature, thinking about catalyst, and remember, with a catalyst, it is a reactant that causes a different set of reactions to occur. But we end up with the same products. So we go through a different set of reactions, but we get to the same place. The reason why catalysts are used is that a catalyzed reaction has a lower activation energy than non-catalyzed. So catalyzed reactions have lower activation energies. And the last one is only for solids, and that is surface area. So we've done collision theory, we've done reaction rates, and now we're going to get into a little bit more of the mathematical piece. One thing I want you to know is you do not need to know anything about chemistry for a reaction to happen. Chemical reactions occur whether we think about them, study them, write about them, sing about them, do anything. And so chemical reactions occur whether we study them or not. that's sort of the first thing I want to have you sort of get thinking about, is that these reactions happen no matter what. The second piece is that we use chemical equations So we write down these chemical equations to represent the change happening. The third piece is balanced chemical equations. Are needed to calculate any sort of variable. Oops, of, not or, of number associated with the reaction. So writing down this chemical equation and then taking it a step further and getting to a balanced chemical equation. Oh my goodness. We only need it for calculations. When we balance these chemical equations, there are a couple of things that we're going to be looking at making sure we have. Okay, the balanced chemical equation, it ensures that the reaction follows the law of conservation of mass, or the law of conservation of matter. Coefficients are multipliers. So we're going to be using these coefficients to make sure that there are the same number of each kind of atom in the reactants as in the products. So let's see how this works. During respiration, glucose reacts with oxygen gas to produce carbon dioxide and water. So that's the chemical change. All right, so let's see here. Glucose is C6H12O6 plus oxygen gas. Oxygen is one of those lucky seven that shows up as a partnership, those diatomics, and it makes CO2 and H2O. Again, glucose, oxygen, carbon dioxide, squeeze it in, and of course, water. Our balanced equation is going to be this. 1 C6H12O6 plus 6 O2s go to make 6 CO2s and 6 H2O. Numbers out front, 1 to 6 to 6 and the 6. Those are the multipliers. Those are the coefficients. You do not have to include the value 1 if you don't want to as a coefficient. It's not necessary. Just as a reminder, these coefficients are multipliers for the entire piece. Let's see if I can make it a little more clear. When I have 1 C6H12O6, I have 6. I have 6 carbons, 12 hydrogens, and 6 oxygens. And by writing the 6 O2s, I'm saying that there are 12 oxygens. That's on the reactant side. On the product side, break it apart here. I have 6 of those CO2s. Well, that means I have 6 carbons and 12 oxygens. And then the 6 water mean that, again, I have 12 hydrogens and 6 more oxygen. If I go through and do a little accounting here, remember the top of the squiggly line here, those are the reactants. There's 6 carbons on the reactants side, and there's 6 carbons on the product side. Hydrogens, 12 hydrogens reactant side, 12 hydrogens product side. Oxygens, well, there's 6 and 12, so that's 18 total, and then 12 and 6, so there's 18 total. This is a bit big, cumbersome, if you ask me. So rather than write it out this way, breaking down each compound separately or each substance separately, and then having to combine and say, okay, well, there's 18 oxygens here, and then yeah, I've got, again, 18 oxygens here. Again, it's big and messy. Okay, so let's see if we can't figure out a different way of doing this. Okay, so remember, in terms of just vocabulary, we have reactants, our starting materials, and our products. This reaction arrow is our balance point. So let's count the number of each kind of atom. Or polyatomic ion. Now we get to start to balance. Where do I start? Right, where do I start? So once you have those down, now we get to start to balance. Often, starting with the most complex and going to simpler ones works really, really well. So you're going to look for something that has a lot of elements in it. that has large counts of elements in them. So go from complex to simple. Another one, this is more of a don't. Don't start with an element that is in multiple reactants and products. And if you think about, we've already seen this in the reactant side. We have oxygens from the glucose, and we have, well, oxygens with oxygen. But there's two places where oxygen shows up. And then in the products, oxygens show up in both products. I'm not going to want to start with that. I'm going to want to try to figure out something other than oxygen as my starting point, okay? And then the last one is sometimes you'll find yourself with fractions, or your mind just works to have multiples. We want our coefficients to be in the smallest whole number ratios. Okay. Oh, these are really like numbered. This is step 1, this is step 2, this is step 3. Once you count, once you get that preliminary accounting table set up, then it's just a matter of trying to figure out what multiplication factors you need. So I would say the next thing to recall is that, coefficients are multiplication factors. And they multiply everything in that formula. For example, if we have a compound such as C12H22O11, and I've got a coefficient of 2 in front of it. In terms of counting, for the carbon, well, there's 12 carbons, right? But this is the coefficient of 2. Well, that means that there are 24 carbons. This 2 also goes with the hydrogens. That means we've got 44 hydrogens. And lastly, we have 2 times the 11 oxygens, which means there's 22 oxygens. It gets a little more complex when we work with polyatomic ions and within parentheses. For example, calcium nitrate, CaNO3 twice. And just for lack of anything better, I've got a 3 in front of it. What you may want to do when you're first starting off is break down the calcium nitrate. So in this calcium nitrate, we've got 1 calcium, and then the subscript outside the parentheses, it multiplies everything inside. So that means that there's actually 2 nitrogens and 6 oxygens. And we're going to be multiplying by 3. So 3 calcium nitrates actually means that we have 3 calciums, 6 nitrogens, and 18 oxygens. Third piece, when you change a coefficient, recount all your atoms. I kind of liken balancing equations to following like a set of dominoes. So I'm going to balance, I don't know, whoops, atom, A. Which impacts atom B. So the second piece then would be balance atom B, which impacts atom D. And then you just keep going until you get to that final balance piece. Okay, so let's do this one. Let's try this. Like I said, we've done these before, so I have NaOH and H2SO4, and this gives me Na2, that would be Na2, come on, 2SO4 and H2O. Let's set our accounting up. Na, O, H, and then I get over to the sulfuric acid. I have H, I have S, and then I have O again. Perfect. All set. So now let's see sodium hydroxide. There's just a single sodium. And on the product side, Na2SO4, there's two of them. Oxygen. Let's see. Oxygen, I have oxygen showing up. There's one here and 4 there. Think I have 5. And then on the product side, lo and behold, there's 4 with the SO4, and then there's the 1 with water, so that's 5. Whew, that one's balanced. I'm liking that. Hydrogen, I have 3 hydrogens. One's with the NaOH, and then the 2 with the sulfuric acid. And I have just 2 on the product side, and then sulfur, 1 and 1. So at this point in time, which one are we going to choose to balance first? I could do sodium or I could do hydrogen. Sodium is in one reacting species and in one product species. Hydrogen, on the other hand, is in both reactants. Well, it is in only one product, but it's in both reactants. No thanks. Let's try the sodium. Let's try that sodium. So I'm going to multiply by 2. That means I'm going to put a 2 out in front of the sodium hydroxide. Well, this 2, as you saw above, right, goes for the sodium, goes for the oxygen, and goes for the hydrogen. So my new oxygen count, I've got 2. I've got 2, oxygen. I've got 2 oxygens plus 4 more. I've got 6 oxygens. And now how many hydrogens? 2 hydrogens plus 2 more. I've got 4 hydrogens. I didn't touch sulfur. Okay, so now I can balance oxygen or balance hydrogen. Once again, I'm not going to go with oxygen. Oxygen is in both products. I just put this 2 here to get the sodiums to balance. I certainly don't want to play with this number. If I change a number here, I'm going to change the hydrogen count. I'm going to change the sulfur count. I'm going to change the oxygen count. No. What to do, what to do, what to do, what to do. Well, look, hydrogen's in only one product. So if I put some kind of a number in front of water, I'm only going to be impacting changing the count of hydrogen and changing the count of oxygen. And at this point in time, hydrogen and oxygen are the only 2 that are messed up. That's the one I want to do. So now the lowest common multiple between 4 and 2 is 4. So I'm going to be multiplying by 2. So that means I'm going to be putting a 2 up there. By putting the 2 there, I also have changed my oxygen count. So there's 2 oxygens and 4 oxygens. Last I knew, that made for 6 oxygens. Done. Done, 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 done. Done, done. Let's try this one. Let's see. Na3PO4 plus FeNO3 twice goes to Fe3PO4 twice and NaNO3. Okay, so here we go. I've got Na, I've got P, I've got O, I've got Fe, I have N, and I have O again. All right. Sodium, I've got 3 and 1. Phosphorus, I've got 1. Oh. I don't know where. NaPOFEN and O. There we go. I've got 1 P, I've got 2 P's. Oxygens. Let's see, I've got 4 plus 6. I've got 10. And I've got, oh my gosh, let's see, I've got 8 and 3. That makes 11. How many people think that there's a good probability that people have miscounted the number of oxygens. It's kind of a pain, isn't it? They're in both reactants, they're in both products. Ugh. Dr. Price, you didn't finish the iron and the nitrogen. You're right, I didn't. I didn't on purpose. Let's take another look at this expression. I'm going to rewrite it. Na3PO4 plus FeNO3 twice. Fe3PO4 twice, and NaNO3. Excellent. Notice phosphate, PO4. Got PO4. I've got PO4. It's sticking together as a unit. Right? Why separate it? It's staying together. Doesn't the same thing happen with the NO3? Yeah, it stays together too. If you have polyatomic ions that are the same on either side of the equation, keep them together and balance them as a unit. I'm not even going to look at that. Instead, I'm going to invite you to think about balancing it as Na, or PO4, that's a unit, Fe. And NO3. There's 3 NAs, there's 1 PO4, there's 1 Fe, and there's 2 nitrates. On the product side, I have 1 sodium, I have 2 phosphates, I have 3 irons, and I have 1 nitrate. Pick one. Pick one. Well, since this is first, let's try doing that. Nah, I don't like how that looks. What's the one with the biggest subscripts across the Fe3PO4 twice? This one right here. Let's see if we can't maybe balance the iron and balance that phosphate first. Again, starting from the most complex. They're all pretty ugly. The reason why I think starting here is because both of them are not 1. So I've got a 3 and a 2. There I've got a 3, but that's a 1. I've got one iron there. I've got one Na and one NO3. So start with the largest subscripts. So Fe3PO4 twice. That's the piece with the most craziness going on, I guess. All right, well, if I do that, maybe I'm going to do the larger of these. I'm going to do iron. So 3, so I'm going to multiply by 3. I'm going to toss a 3 up there. Now, by putting a 3 up there, what does that change? Changes the nitrate count. My nitrate count is no longer 2, it's now 6. I want to balance the nitrate. This is what I mean with this domino effect. I picked iron. By balancing the iron, I changed the nitrate count. Now I'm going to need to multiply product side by 6. But by changing this, putting a 6 in front of the sodium nitrate, that messes up there. I'm going to have to go to, that's now a 6. Okay, well now I need to get the sodiums to balance. Well, if I have that as a 6, I need to multiply by 2. So I'm going to put a 2 there. Well, that's going to change my phosphate count. My phosphate count's now 2. Notice what did not get quote unquote balanced. What didn't I have to change? I didn't change the phosphate on the product side. I didn't change the iron on the product side. So my final answer here is 2 Na3PO4 plus 3 FeNO3 twice goes to make Fe3PO4 twice and 6 NaNO3. Done. Again, my approach here was, if we have a polyatomic ion that is the same in reactants and products, balance them as a unit.